Hello, everyone. Hopefully, you're doing well. We're going to continue with chapter two, functions and graphs. In the first one, we just went over some very basic graphs. We tells you when a relation is a function. So we said, oh, you know what? Can you find collect informations from a graph? So we went all of it. All of this, we use the vertical line test. To try to decide or if a relation is a function or not. Of course, we obtain information from a graph, as I said. There's plenty of things we do in the first section. We evaluate functions, and I think you enjoyed. We graph some basic functions we call linear functions. In this one, we're going to continue with with this study, where we would identify intervals on which a functions increase, decrease, or constant, in some situation, like when you flip a coins, you expect to obtain a head or the tails. If you toss a die, you expect to obtain 1, 2, 3, 4, 5, 6. Well, in the market, in the stock markets, there is a possibility that it's increase, it's decrease, or stay the same. Your blood pressure or your blood sugar. Your blood sugar, if you test it, if you take it, there is a possibility it's increased or it's high, it's low, or it's the same. So, we can identify interval for all of this. We're gonna use a graph to locate relative maximum and relative minimum, or relative maxima for plural or minima. We're going to test for symmetry. Symmetry is like when you can split something 50-50. Even identify even or odd functions and recognize their symmetries, understand and use piecewise functions, very important to verify, and find and simplify functions different quotients. So of course we're gonna go over all of this, and I'm pretty sure you would enjoy doing that. For functions, as we said, it can be increase or decrease, and sometimes you use your intuitive understanding of ways to describe a graph. You just look at it and you can describe it. But sometimes it's important to use some regularity. So a function is increasing on an interval I if f of x is less than if f of x sub 1 is less than f of x sub 2 whenever x1 is less than x2. If we go with the first one, what we mean by that, this is an xy point. Suppose I have x1. When I plug it in that functions, it gives me a y that I would call f of x1, right? And we have an x2. So for the first one, it gives me a point right here. When I have an x2, when I plug it in the functions, it gives me, for example, an f of x2. As you can see, if I graph these 2 points, if I plot these 2 points, it's an increasing function because we rise from left to right. But if I take the same thing, if I go with a functions where if I plug x1 in the functions, it gives me f of x1 right here. And if I plug x2, for the first one, we have a point here. For the second one, probably it gives me a point right here. So that f of x2. And you see, this is a decreasing function because despite x1 is less than x2, you see f of x2 is less than f of so, or f of x1 is greater than f of 2. So it's decreasing. Or if it's constant, despite that you have x1 less than on x2, where you have both of them on the interval, then it would change. Suppose, for example, you have x1 here, x1 here. When you plug it, probably it's gonna give you f of x1, and when you plug x2 in that function, it's also give you another point. That's right there. So because f of x1 equal f of x2, we're gonna say it's constant. There is no change. So in the stock market, it's either increase, decrease, or stay the same. All right. In your blood sugar, it's either high, low, or stay the same, which is very important. Look at what I said in some other examples. You see the first one right here. If I call it a, is an increasing function. If you look at this one, is a decreasing function. I'm gonna call it b, and c is a constant. Either you see there is a hole, a dot that has a hole, so the endpoints not included in this study. Now, looking at these functions, okay, state the interval on which the graph, the given function is increased, decrease, or constant. All right. So we're gonna look through it. First of all, increase. For me, I feel like it's increase from down here going up to what? Okay, let's suppose it's negative one. So we have the increase, the functions increase on what interval? Yes, negative infinity to negative one, right? If you agree, right? Now, where it's increasing again, because I can see increasing somewhere else. Yes, I can see increasing here, right? It goes up. If I want, I can say, I'm gonna write it down, so because I can put oh, okay, first of all, you can just put negative infinity, -1, and you can say that it is negative it's 1 and infinity, or you can say negative infinity, -1 union 1 infinity. That's why it's increasing. Where do you think it's decreasing? Please verify. It's decreasing. Yes, the only place it's decreasing is right here between -1 and 1, right? It's decreasing on -1 and 1, right? So we can look at the graph. We identify where it's increase. Increase, that means it's rise from left to right, or it's decreasing if it's fall from left to right. But there is no interval in which it is constant here because we don't have a straight line horizontally. So unfortunately, we cannot say it's decreasing. All right. Now, some of the examples we can see, or definitions we can see, of course, it's about relative maximum and relative minimum, or we can say relative maxima and relative minima, the points at which a function change its increasing or decreasing behavior. We can, we use it to find the relative maximum and relative maximum values, So if you look at the previous examples, you can say relative maxima was at the point it's changed right here, or at the point it's changed right there. The change, it's increasing or decreasing behavior. That's how we call it. Now, look at what we call as definitions of it. A function value f of a is a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x, okay, for all x not equal to a in an open interval. So you see right there, it's a relative maximum right there. Relative maximum is the highest peak you can go, all right? And a function value f of b is the relative minimum. This is the relative minimum right there. Relative maximum here, relative minimum here. Okay, I don't know why I keep saying here. Maybe you might not see what I'm talking about. This is a relative maximum, the highest point we can go. Do not look at the arrows. The arrows doesn't give you the math. If you have an endpoint, yes, with a closed dot, then it would be minimum maximum. But here, the arrows doesn't express it. Or you can say that you have a relative minimum down here, the lowest point you can go. All right. So the word local is sometimes used instead of relative when describing maxima or minima. Of course, my students in calculus understand exactly what I'm talking about when we use local maximum, local minimum, absolute maximum, absolute minimum, relative maximum. So of course, but you'll have time, we have a chance to talk about it closer. And examples, what about that? So identify the relative maximum and minimum for the graph of x. So right there, we only have two of them, right? So if they ask you to identify that one, where do you think f has a relative maximum? Okay, I'm gonna write while you're thinking. F has a relative maximum at x equal what? Yes, x equal -1, right there. This is the maximum we can go, all right? And what is that relative maximum? So relative maximum is what? Is if you plug -1 in your functions, what would you do obtain? Yes, 10. 10. You can see that. This is 10 right there. So it's 10. Okay. Now I'm gonna write down while you're thinking. F has a relative minimum, okay, at what? What would be x? Yeah, x equal 1, right there, right? The minimum is that point. So what is that minimum? Yes, minimum relative minimum is what? Yes, -10. You can see it right there. It's negative, right? So you go the lowest point for the absolute, or you take all the minimums you can have. Some example has more than one minimum, so it's fine. You can verify that. All right. That's something we need to check about. We're gonna go over a table that defines three common forms of symmetry because we need to talk about symmetric as well, right? Because symmetric is something we're gonna have to deal with the number of time, you know. When you look at the eyes, even for the eye, I don't know if you ever go to the eye doctor, they kind of said, look at straight and tell us the letters you find, you know. Certain objects of people are so well balanced and proportionate that they are universally pleased to the eye, you know. Yeah, that's poetry, I can say. Do you know that graphs of some equation exhibit exactly the kind of symmetry you can see? You know, like when you take a parabola, you can split the parabola half. If you take an absolute value functions, you can split it half, okay? So you symmetric with respect to the x-axis or to the y-axis. It all depends on what type of graph you have. Let's define you know, three common forms of symmetry and gives rules to determine if the graph of an equation is symmetric with respect to x-axis or y-axis or to the origin. So if you consider an equation in the variable x and y, we say the graph of the equation symmetric with respect to the y-axis if for every point xy on the graph the point -x, y is on the graph. That's a certain way to explain it. And of course, you are in the practice, we're gonna do more on this. If you substitute -x for x in the equations, and you see that, well, if we substitute -x, you know, in the equations, result in equivalent equations, then you would say it's symmetric with respect to the y-axis. But the graph of the equation symmetric with respect to the x-axis, if for every point xy on the graph, x negative y is also on the graph. So substitute -y for y in the equations result in equivalent, all right? And also, we're gonna say if it's symmetric to the origin. What's happened? Let's see the next slide. I think it's origin, right? The graph of the equation is symmetric with respect to the origin. And for every point xy on the graph, the point negative x and negative y is also on the graph. So make sure these 2 points are on the graph. If it's happened, then you conclude it's symmetric with respect to the origin. A lot to see in only one example. So we're gonna use probably 1 or 2 examples, but look at these examples. We said determine whether the graph y equal x squared minus 1 is symmetric with respect to the y-axis, the x-axis, or the origin. First of all, we need to verify if it's symmetric to the check symmetry to y-axis. So if you check symmetric to y-axis, the first thing you need to do, substitute negative x because that's what we said. Y-axis, where is it? Y-axis, you need to substitute negative x for x. So that means, this one, for xy, you're going to substitute negative x, y. When we do, when you do to the y-axis, right? Is that y-axis, right? Yep, negative x, y, negative x, y, all right? When you do to the y-axis. So I go back in the equations, I substitute, I said y. This is the equation we have, x squared minus 1. Now I'm gonna do y equal negative x squared minus 1. That should give me y equal x squared minus 1. What happened here? Do you agree the equation, these two equations don't change? I mean, the equation doesn't change despite we substituting x1 negative x, then it doesn't change. The equations is the same, right? The equation is the same. So no change. Okay, the equation is the same. So the graph is symmetric. So the graph is symmetric to the y-axis. Well, if you want to try the other ones, that's fine. But for certain, if it's symmetric with respect to the y-axis, then the other two won't work. But you can still verify if I copy and paste the same slides, and you can eventually try, if it's symmetric to the x-axis, okay? Symmetric to, because that's what we said, symmetric to the x-axis. So what we said about x-axis again, remember that? Is symmetric with respect to the x-axis, x-axis, if you substitute negative y for y, right? So if you do, like, you have xy, it's gonna give you x negative y. So we know that's not gonna happen when it's you have y equal x squared minus x, now minus 1, sorry. So to do negative y equal x squared minus 1. So if you multiply both sides by negative 1, you're gonna have y equal negative x squared plus 1, and that's not equivalent. So no, not symmetric, right? Because you don't obtain the same equation. So not symmetric to the x-axis. So it's gonna be symmetric only to the y-axis because you cannot have it symmetric to both. We already see it's symmetric to the y-axis. Then even though you substitute both of them for the constant one, substitute negative x for x, negative y for negative y. It's not gonna work. Okay. If you're okay with that examples, I think we're ready to do better than that because I know you can, do it when substitute to the origin. So, yeah, I think I can do that right there. If we do to the origin, I'm gonna just erase here. I think all of this can be check symmetry to the origin. Now, what we said to the origin, substitute negative x, negative y for xy, right? So if it's to the origin, negative x for x, negative y for y in the equation, y equal x squared minus 1. Negative y for y, negative x for x. So that still be negative y equal x squared minus 1. If we multiply both sides by negative 1, we're going to have y equal negative x squared plus 1. Again, the equation not equivalent. The equation not the same. They are not the same. Because it's not the same, so not symmetric to the origin. The only times you find the same is for y. Okay. The first one, yes, the equation is the same, then it's symmetric to the y-axis, but not to x and to the origin. Hopefully you like that examples, of course. And we promised that we were going to talk about even and odd functions. Very easy to remember even functions. In a functions, if you substitute x for negative x, the function would never change. If you substitute x for negative x and you find negative f of x, then it would be odd. So you have these two conditions in order to conclude if the function is even, then f of negative 1 equal f of x, f of negative x equal f of x, or it's odd if you plug negative x in the function and give you negative f of x. So the graph of an odd function is symmetric with respect to the origin. The graph of an even function is symmetric with respect to the y-axis. All right. So that's would help you to save a lot of time if you can remember it that way. Okay. So yep, it's gonna help you to remember it that way. Even functions, remember that we said even function f of negative x equal f of x. The right side of the equation of an even function does not change if x is replaced with negative x. That means nothing changed. But odd functions, every term on the right side of the equation of another function change sign if x is replaced by negative x, or neither, the right side of the equation change if x is replaced with negative x, but not every term on the right side change. All right. So we're gonna see that here we have a few examples we can verify. The first one, we have plenty of them actually we can try. Among them, we see that we have f of x equal x to the 5th power plus 1. Let's see if it's even or odd. Okay. For a, I'm gonna put a here. F of x, h of x equal x to the 5th power plus 1. So if we substitute, first of all, you need to substitute and find h of negative x. So negative x power 5 plus 1, that gives you h of negative x equal negative x to the 5th plus 1. Now you see h of x is not equal h of x is not equal to no, h of negative x, okay? H of negative x is not equal to h of x, and h of negative x is not equal also to negative h of x. So what is it, odd or even? No, it's neither. The function is neither. Neither odd or even, all right? It's neither odd or even. That's some point how you're gonna qualify an example like this one. But if you look at B, I can even do B here for you. If you plug f of negative x, here it gives you negative x squared, negative x power 2 plus 6. It gives you f of negative x equal x squared plus 6. I believe because as f of negative x equal f of x, we substitute x for negative x. You see the function stay the same. It doesn't change. It still gives us x squared plus 6. So it, what would you say is this one here? Even, because symmetric with respect to the x-axis. So it's even, and remember when it's even, it's symmetric to the y-axis. Symmetric with respect to the y-axis, okay? Now, let's see for C. If you do g of negative x, let's substitute 7 times negative x power 3 minus negative x. Remember, a negative number power an odd number give you negative. So we're gonna have g of negative x give us negative 7x power 3 plus x, minus minus to go plus. So do you agree g of negative x, I can say negative, I can factor negative, is gonna give me 7x power 3 minus x. See? For me, it's like I have g of negative x equal minus negative g of x, right? So it's what? Odd or even or neither? It's odd. It's odd. Okay. So because it's odd, okay. So remember it's odd. So it's symmetric with what? X or Y or origin? Is symmetric with respect to the origin. Symmetric to the origin. So don't forget to stop and go back to the previous video slide to make sure you understand when we said every times you substitute, it can be with the graph of an odd function is symmetric with respect to the origin of an even function, symmetric with respect to the y-axis. Okay. I think you have questions, but unfortunately, you're not here to ask me these questions. So that's why I'm gonna just move forward to piecewise functions, because piecewise functions is another beautiful one that you probably heard before or you use it before. Usually is making decisions. We can split our functions into two functions. A function that is defined by two or more equations of a specific domain is called a piecewise functions, right? Very easy, to define that. So many internet plans can be represented with a piecewise functions, right? Um, we can do that. A cell phone company also had the following plans, for example. I think that's the next example. Uh, you know, if we call it this way, we can call it a cell phone company, or we can call it a different ways. The most important is like you get what we mean. If we have a cell phone company, that give it this way. Or if we don't want to call it a cell phone company, let's see. We have a function. They ask you to find f of, for this one, you must find f of c of 5. We call the function c. Remember, what is c of 5? Now, our questions, remember, if g, for me, g here equal 5. Look where g is located. Is it located on the first interval or the second interval? That's the question you need to ask. Because we said if g is from 0 to 15, we know the value for that function will be only 40. But if g is greater than 15, then you need to use the second equation. Because here we have two equations. The first equations we have c of g equal 40. And you have a second equations where we say c of g equal 40 plus 0.60 times g minus 50. You want to substitute all g for x and c for f, we try to. We can call it f of x, but we want to play with those numbers. Now, because g equal 5 is in this first interval, because g equal 5 should be somewhere here between 0 and 5, we know c of 5 is simply 40. But c of 50, because c of 50 is right there, because remember g is 50 here, so it's gonna be in the second equation. Because it's in the second equation, we're gonna do c of 50 would be 40 plus 0.60 times 50 minus 15. That would be c of 50 would be 40 plus 0.60 times 35, if you agree. That would be 40 plus what? 21. So c of 50 would be 61. And that's it. Very simple one. We can have different names for it, but at this point, let's call it a piecewise functions, all right? Another one you can probably do, here they ask you to graph. We can graph piecewise functions, of course. First of all, they ask you to graph the first one. Let's do the XY plane on this side. This is my XY plane, okay? When they ask me to graph that functions, first of all, the first one, they said if x is less than -1, that means x cannot be less than or equal to -1. This is x. This is -1. Less than or equal to. So it's going to be a closed dot because it's less than or equal to. So what I'm going to do here, I can even do a tables because we can take any number for x below -1. So if x is -1, if x is -1, you know it's gonna be 3. If x is -2, because there is no x to substitute in the first function, because you have two functions of f of x equal to, it's just a constant. That would be 3. If x is -3, it's still gonna be 3 because no x to substitute. So we're gonna have 1, 2, and 3. So if x is -1, we're gonna have 3. If x is -2, we're gonna have 3. If x is -3, we're gonna have 3. So as you can see, we're gonna have a constant function, right? It's gonna go this way. And we can continue indefinitely, but it's close and stop at -1. Now, if we decide to graph for the second one where f of x equal x minus 2, remember here they said we need to start with anything if x is greater than -1. Remember, if x is greater than -1, here what you're gonna have, that's give you -3. But we can take greater than that, that means we can take 0, that's give us -2. If we take 1, that will give a -1. If we take 2, that would give us 0. If we take 3, that would give us 1, etc. Now, if we try to graph that one down here, remember it's -3, all right? That -3 here would be a whole, because -1 cannot give you a 3 and a 3 and a -3. So that's why, from here, it would be, there is a hole in that dot. Okay, that means -1 is not included. Now, if x is 0, y is -2. If x is 1, y is 1. If x is 2, y is 0. If x is 3, y is 1. Okay, so you see, this is the other branch of our graph, right? We call it piecewise functions, right? We call it piecewise functions. Please feel free to do it any times and make sure you got it correct, okay? Very, muy important. That's very important, okay? Piecewise functions. Some other basic functions, questions about it. So we can define definitions of the difference quotient of the functions. The expressions, for example, um, what we're gonna do in section 2.4, we will study the average rate of change of a function. So a ratio called difference quotients plays an important role in understanding the rate at which function change. But as I said, we're gonna go over this one. So the expression f of x plus h minus f of x over h, for h not equal to 0, remember the denominator cannot be 0. The different quotient of is called the different quotient of a function f. All right. Very simple. We can evaluate and simplify functions like this. If we have f of x, for any reason we have f of x equal negative 2x squared plus x plus 5, is find and simplify the expressions. All right. The first one look easy because anywhere we have that, remember here they only ask you to do something very simple. Everywhere I see x, I would replace it by x plus h. For example, I'm gonna have -2 times x plus h. I believe we do that in an example already. X plus h plus 5. Now, need to remember what to do with a plus b power 2, because we did it in the previous examples, and I'm pretty sure you can remember how to do it in these examples again, because we said if you have a plus b power 2, it would be a squared plus 2ab plus b squared. So this one gonna be -2 times x squared plus 2xh plus h squared. I'm gonna erase because I cannot do all of this in okay, let's do it down here. We're gonna have -2 x squared plus 2xh plus h squared plus x plus h plus 5. If we distribute the -2, -2x squared minus 4xh minus 2h plus x plus h plus 5. Is that something we can move? I'm trying to see if we can move that. Yeah, we can. Yes, we can. All right. This one, when we simplify, would be -2x squared, because there is nothing we can combine with -2x squared. Okay, we cannot combine any of this. So we're gonna leave it like this. -4xh would stay like that, but we have -2h plus, oh, that would be -2h h squared. So there should be, that should be h squared negative 2h square. Oh, we cannot simplify. There is nothing to simplify actually. Plus x plus h plus 5, right? Now, when h is not equal to 0, I would definitely let this one for you to try. And you contact me. If you have concerns and you don't understand it, it's kind of tricky to you, and let me know. So enjoy, have fun, and let me know if you have any questions. Take care.